The event at hand on the left on the top of the screen implies at least one of the two events on the right. Okay, so we want to compute a probability. Monotonicity of probability measure tells you that if you have a bigger event, you get a bigger probability. So the probability of the event on the left is certainly no larger than the probability of the event on the right. But on the right, I've got a union of two events. Call them temporarily A and B. The probability of A union B, on the other hand, by what we call Boole's inequality, and this will take you right back to the basic properties of probability measure in Tableau 5. By Boole's inequality, the probability that one or the other or both events occur is bounded above by the sum of the event probabilities. Identify A with the first event on the right, B with the second event on the right, and we immediately get an inequality. Oh, this is lovely. Okay, and it looks like we have complicated matters, but we've really, really simplified it. And one more step will make it completely transparent. We've got two probabilities on the right. How do we deal with this? Well, we realize that both Sn and Sn prime are statistically the same. What I mean by that is they are both governed by the self-same binomial distribution. And if that is the case, the probability law governing each of them, Sn and Sn prime, is exactly the same, which means the probabilities being queried must be identically equal. And therefore, we simply get twice the probability of, let's say, one of them, say the first one. Now, this is getting simpler and simpler. The expression on the right in the probability looks very familiar. And for a reason. We've seen this before. It asks, what is the probability that the accumulated sum of Bernoulli trials, the accumulated successes, differs from its expected value by some amount? But this is exactly the probability in the tails of the binomial distribution. We know the distribution is going to get concentrated around the center, so this probability should be small. And indeed, Chebyshev's inequality gives us an explicit characterization of how small. Right? So we just run Chebyshev's inequality through here, and here observe that the number delta, the discrepancy that we know from our experiment, divided by 2, plays the role of the error parameter epsilon that we had in Chebyshev's inequality. Plug it in, and we've got now an elegant and simple answer. The desired probability that in my Gedanken experiment, the relative frequencies of successes in the two groups exceeds the stated discrepancy is no larger than twice a term given by Chebyshev's inequality. Now let's simplify, right? When you expand out delta over to the whole squared, you get delta squared over 4. 4 cancels out, and now we've got a really elegant and simple estimate. The desired probability is no larger than 2 divided by n times delta squared. We'd have to be a very demanding customer if we wanted something even simpler than this. This is beautiful, elegant, and simple, and immediately it gives rise to a pronouncement in terms of what our test is supposed to do. Here's what we've got. A probability of a deviation is no larger than 2 over n delta squared. Remember, delta is a known discrepancy between the patients getting the drug and the patients getting the placebo. If you want to evoke some of the notation we've used earlier, then n times delta plays the role of our error, delta is the error, and the expression on the right should then play the role of a confidence parameter, a delta, where 1 minus delta is the confidence. Without further ado, let's just call it a lowercase delta. This is the confidence parameter. Now, here is the basic setting. The estimate on the right tells us the chances that random fluctuation gives you a discrepancy as bad or worse than what is actually observed. What can we conclude from this? We can conclude in 2 directions. One, what if this fraction is small? What if little delta is a small number? a small value for little delta implies, for example, let's say little delta is 1%. It says it's rather unlikely that chance fluctuations will give rise to a discrepancy as big as we have seen. This then suggests that the drug is actually causing complications. It is enhancing the risk. The chance of getting such a large discrepancy by accident is small. So a small bound suggests that there is a serious chance that the drug is causing complications. On the other hand, if the value for the bound, the confidence parameter, is relatively large, say 50%, 40%, something like that, then such a large discrepancy as what we observe in our patient pool is easily explicable by just random chance fluctuations. Life happens. Nothing is certain. Of course, we do have to be a bit cautious with the second part of this pronouncement, you see, because I have not given you an exact estimate, an accurate estimate of the probability. I've given you a bound. It is conceivable that the bound is too loose. It's a poor bound. So a large number might not really say that the probability is large. So if you want to tweak that argument a little further, get a more accurate and definitive pronouncement, then we'll want to get a more accurate estimate. I will defer that, right? But at least we have now a suggestive direction for endeavor. We compute this likelihood, and it's encapsulated in a fraction. If the fraction is small, we have reason to believe that the drug causes health complications. If the fraction is large, we have some reason to believe that the drug is incidental. It does not do anything damaging. And so here we have a slogan. The smaller the fraction, 2 times the reciprocal of n times the observed discrepancy squared, the smaller this fraction is, the more likely that the drug in question exhibits significant enhanced side effects, for example, cardiac arrests, of the type being tested. Again, it is hard to imagine a simpler and easier pronouncement. Now, before we proceed, it might be well to do a little sanity check and a test of your understanding. So let's try this. Consider 2 settings. One where you have a sample size of size 100. So you have a double sample of 100 and 100. 100 given the drug, 100 given the placebo. And you observe a discrepancy. So what discrepancy level can you conclude that there's a 50% confidence that there are, in fact, side effects from the drug? At what discrepancy level can you conclude that there is a 90% confidence that the drug causes side effects? Do it again if the sample size is bumped up from 100 to 3,000. Pause the lecture, scribble with it, try to get your head around these concepts and see if you can come up with numbers. Restart the lecture when you're ready. All that is requisite is to plug into your favorite calculator and the values for little delta being 1 minus the confidence parameter, right? And the value for n. So let's do this without further ado. Suppose n is 100 and the confidence parameter is 50%. In other words, we want a confidence of 50%. And so delta is now 0.5. We find that the discrepancy, big delta, is now 0.2. What if we increase the confidence demand to 90%? In this case, 1 minus delta is 90%, or 0.9, so little delta is now 0.1. Plug it into the expression, and we find that the discrepancy now becomes 0.45. In other words, if our confidence demands are quite small, then a relatively small discrepancy will trigger it. If our confidence demands are high, then our discrepancy creeps outward. What happens if we increase the sample size? If we go from 100 to 3,000? Now, before you take a look at the number, we should understand what increasing the sample size does. When you increase the n, remember the binomial gets increasingly concentrated right around its expected value. In other words, it gets highly likely that Sn and Sn prime both behave very similar to each other, both close to n times p. So the difference is going to be very close to 0, which then makes even small discrepancies harder to explain by random fluctuation. So a discrepancy of 0.04 is already rare when the sample size is 3,000 if you want a confidence of 50%. But if you want a confidence of 90%, it creeps up from 0.04 to 0.08. Let's step back. Okay. So what have we really done? What have we achieved here? We've articulated a systematic process for checking the bona fides of a new putative wonder drug. We're asking, does this drug cause side effects of a particular type? And the test involves simply running a patient pool, one given the drug, one given a placebo, under suitable safeguards to govern bias. The test itself is simplicity itself. All it requires is an understanding of how much the discrepancy is, and that's an easy calculation, and asking how much confidence do I need to enact policy. And out of all of that comes an immediate conclusion. At this point, we should ask, where do we go now? Quo vadis? I mean, this is interesting, it's beautiful, a relatively elementary argument. Yes, we did work hard to get here, but if the student will go back and take a look at it, she will realize that the mathematics wasn't that hard, and step by step it was just essentially a few simple algebraic steps. The results of the analysis give rise to very elegant and easily implemented policy prescriptions. We can do polls, and we can even test drug efficacy. Now, at this point, the sample size requisite are modest. If you remember, when we were doing a poll, to get accurate estimates, say for about a 3% error with a 95% confidence, we needed, by our estimates using Chebyshev's inequality, something like 5,000 sample size. 5,000 individuals give us good estimates. When we moved to drug testing, we were laboring under the problem that not only did we not know the underlying success probabilities, but we were comparing a double sample. You see, we were comparing a probability for the drug with a probability for the placebo, both of which were unknown. And so we end up effectively estimating the probability for the placebo while we're doing our experiment. We're going to have to pay a price for this double estimation. And this price is manifested in the factor 2 in the numerator of our bound. So roughly speaking, our sample size will double to get the same kinds of confidences we had when we were doing just a poll. Which means that if we needed 5,000 individuals to get a reasonably accurate estimate for a poll, we're now going to need 10,000 individuals. Now, at one level, that's encouraging news, right? It's a fixed number. At another level, this is very disquieting. I've told you how expensive this process is. 10,000 individuals will cost an enormous amount of money to monitor, to check, to recruit. And so there is an incentive here to see if we can improve the bounds, reduce the sample complexity demands on a process. 10,000 is a lot. Can we bring it down to something more manageable? So this is one profitable direction for inquiry. And this is going to lead us to the fabulous bell curve. That is the subject of our next tableau. A second direction for inquiry is Chebyshev's inequality worked beautifully for the binomial. I wonder if it perchance could work in other settings. This turns out to be a very rich and profitable direction for inquiry. And this leads, among other things, to new procedures and algorithms for computing very complex, very large problems. This will be the subject of our next mini lecture.